Okay. From CSCS. Sorry? Oh, yeah.
So now in this parallel file system round, we have the third competitor here, BeeGFS. So Hussein Harake from CSCS is going to talk us about BeeGFS.
Okay, so thank you very much for inviting me. It's really a wonderful place. I had some difficulties flying to here, but luckily I'm here. I'm just happy to be here. So first of all, I'm a customer. So I don't do marketing, I don't do anything. So I will just be asking the same way I ask the BeeGFS guys or Luster or GPFS to be the same for me. What I care about, just sharing with the community, everything we learn. So what I'm going to talk about today is just more than what the title is. I will be giving talk a little bit about what we do actually at CSCS, and especially in our unit. At least if I can travel again and again, they will just sponsor something, and then I will go to this case of the BeeGFS. And please make it interactive. I like to have like an interactive discussion. Okay, so CSCS, founded in 1991. I joined CSCS in 2001. So far now 16 years at CSCS. I started the HPC part in 2005. We're starting managing the first Cray machine at CSCS at that time. And I can tell you at that time, in every reboot of the system, we had to rebuild Luster. So just imagine how it was. Part of ETH, I think I won't say a lot more here. I think that's enough about CSCS. The machines, when it started, I believe we had the NEC SX. It was a vector machine in production for the climate code that was running there. It was the NEC SX4, I believe. At that time, also 3 was just backup. Then we got the IBM. And 2005, we started with the Cray XT3, which was the first massive parallel machine at that time. Now we have PitchDite is the biggest machine. I think these numbers are quite. There's one part of it is not visible actually in that picture, which is the new one, which is up to 7.7 petaflop. I think just generating the PDF just missed that part. And this is a hybrid machine, so we have an accelerators inside it, and so it has the Haswell processor and the P100 from NVIDIA. Okay, so when we talk about HP centers, usually we talk about computing. That's how it used to be. Now it's not the case anymore. So we talk about HPC system, and you talk about infrastructure. So directly, how much power do you have? How do you cool your system? And these are typical problems in big centers like CSCS. So what we have, I believe we are using around 1.2 megawatt of power. 1.3, we can go up to 16 megawatt. And for cooling, we use the water from the lake. So we are pulling the water at 30 meters down from the lake at 5 degrees, crossing the city of Lugano, which is around 5-6 kilometers, coming to our center, and just going back. So this circuit is just the open one, and this is how we cool 2 other circuits that we had internal at CSCS, closed ones. And so just imagine, this is the amount of liters per second, this pump could just deliver. That's the peak performance, 700 liters per second. So if you have a swimming machine, if you have a swimming pool, it will take, even to warm this to 45 degrees, it will take around, if we have 150,000 liters that they are reserved internally, and this could be warmed in 5 minutes using PitchDite.
How hot is the water when you return it?
Okay, so when we return it, we return at the surface. So it's not down on and the way back, it will get cold. It's just the temperature will go down, And going to surface, we have like around 3 to 4 degrees should be going back to the surface different from the temperature of the lake. So it's like, let's say if it is 25, we can go up to 30 maximum just to bring it back. We'll never bring it back 45. The green people gave us a hard time really before they allowed us to make this all infrastructure. And this is a machine room, so which is around 2,000 square meters. It's just like the soccer camp, actually. Okay, so I work in a unit called system integration. So we do many things, actually. One of them is just managing projects, relation with vendors. So vendors should contact us, actually, not go straight to the operation. Evaluation technologies, and this is where I'm mostly involved, actually. And there are some development going on in software, especially with containers, Docker, and this kind of development. So this is our cluster. Well, actually, these are 4 racks that we are using for evaluation. I put this picture here just to show you the kind of technologies that we have. And it's like a Frankenstein machine, to be honest. So here we have, these are from DDN storage. These are the WAS system, and I will talk a little bit about it. Here we have an embedded cluster from DDN, and here we have a different system where we have BeeGFS sitting. So we have Luster, WAS, which is in object store technology, and we have Luster and BeeGFS here, and we have here actually, here we have GPFS. So every client in this cluster, it has GPFS, Luster, and BeeGFS, and all of them they are working in parallel. You know, and we have EDR and Ethernet and plus Omnipath here. So some of them are connected to Omnipath, some of them connected to EDR, and all of them the 100 gigabit. We have also 100 gigabit Ethernet, and we boot over the 100 gigabit. So just the Pixie boot goes over 100 gigabit or it goes over IB. And I can simply tell you there are many reasons for that. So we had cases where we need fast Ethernet, we had cases we need IB, where IB makes a lot of sense, where we need a low latency for MPI, where some cases only bandwidth and we don't care about latency, so we'll go Ethernet. So it depends on the case and the use, and we'll show you why all these cases are important in all these technologies. Beyond that, the kind of storage and network that we have, and we have also 10, 40, and 1 gigabit. That's all included there. Now, for accelerators from the K20 up to the P100 are there. So K20, K40, K80, P100, all combinations are in this cluster, in this system. And at the top of these, we have one cluster called Grana, and we have the OpenStack cluster here, which is called different cluster. I will show just one graph about it. So all this environment, you know, having all this environment, including one more thing I missed, which is actually these are here the power nodes. These are the Minsky nodes that you just mentioned. And we have this system from, this one is an ARM from the Cavium, so the Thunder X. So all of these are managed, you know, somehow quite interesting to manage and having all these technology. That's why I wanted to show this. There are still some more technologies inside these 4 racks, but I think some of them I cannot talk about because are under NDA. For instance, we have some Skylake here in this system, but the only thing I can say is that we have a Skylake. Okay? Oh. Okay. So that was quite fast, actually. One click. Okay, so IME. This is the first technology I will be discussing about is the IME, and we have been testing it for a period of time, and we did a lot of work with it. What's IME is just simple. It's a caching layer that sits between the parallel file system and the application. So the application will not write to the parallel file system. It will write to this caching place. You can talk POSIX, or you can use the library, the IME library, where you need to compile an application with the IME library. And the advantage is that you use the high-speed hardware with scale. The software scales with the high-speed hardware, which is, we cannot see a similar scaling level with the parallel file system. I mean, you can change, you put NVMe SSDs on Lustre and you start creating files, you will see that it will not scale with what they have in the background, the hardware. And that's the same applicable to every hardware. So we'll always be hitting a certain limit because of software, because of different reasons. And it gave some advantages. How it's just still here. It gave some advantage for us where we have seen we were able to sustain it. So we run it in 4 servers, and they were populated. Every server was 24 SSDs. So we got from these 40 gigabytes per second sustained on these 4 servers. And that was sitting, and we were running on, and in the background we had Lustre, and it had a hardware that goes up to 3 gigabytes per second. So we were running up to 40 gigabytes per second, and then in the background, just a policy just synchronizing with the file system. And the same goes for accessing data and just pulling data from the file system. That's only one slide about the IME. That's also about WAS. WAS, what it's an object store. It is what it allows us just to share data between 2 sites and synchronize these data. So you just, if you use a client like S3 client or whatever the client you are using, pulling up, just put data on the object store, then you can pull it from the other side. Also, I've just here, I will show just little simple. This is we're using a gigabit actually, and you can see just the bandwidth is what was quite low. And then when we start changing the network, we went from gigabit to 10 gigabit. We start seeing just going up, and here I believe this is around 400 megabytes per second. And then again, when we change that again to 40 gigabit, because it works only in Ethernet, we start seeing that, and here we have seen like 2 gigabytes per second. I mean, the hardware behind just goes up to 3 gigabytes per second as an object store. OpenStack, they've been doing a lot of work actually on it. I believe this is the last one before I go to BeeGFS. That was quite interesting actually for us. We did a lot of work on the OpenStack. Any here just use OpenStack? Okay, not a lot actually. So the OpenStack, if you look at any layout of an OpenStack system, you will see 4, 5, 6, 10 subnets. And for every service, they will put a subnet. This is 1 or 10 gigabit. And this is a typical industrial solutions for deploying an OpenStack. Now, when we started it, we said, okay, why I need to have, let's say, 6 subnets and making my network so complicated? How we can just bring HPC there? So what we can get an advantage from the HPC network? And the first thing we came out with is, okay, I will just remove all the subnets, and I will just make one subnet. I will pick 100 gigabit Ethernet instead of having multiple ones. And I will just use all the services from database to the object store APIs to the virtualization and starting the instances using the same network. And I had long discussions with architects from Red Hat, from different sites, and they disagreed. No, that's not going to work. We'll have a lot of problems. And now we're in production for like the last 6 months. We have never seen a problem. And what we're using here, we're not using 100, we're using 40 gigabit Ethernet, actually. Yes.
Have you seen any concerns from the users regarding privacy? Or you don't care about that?
We did not see that at all, actually, because these are the users that we have. They are just already our customers, and they know exactly where their data are ending up. And so far, at the moment, we did not see any issue with that at all.
Because one of the main reasons why you want to have this complex node-on is because usually customers wants to have full control on the network that they are setting up, and you don't want to share with us other stuff that other people are running the same.
Yeah, if you have a multiple subnets and you have 2 users will be obliged to go to the same subnet. So because virtualization to go to this subnet, and so they are sharing it. So I'm not when we separate the subnet, we separate it when I create my subnet and use my own subnet, which is for the user. So it's not the physical hardware, it's more the virtual subnet where it could be divided. I might see some, in HPC, I might see problems between MPI and storage. That's what used to be, but now it's not anymore an issue. We did not see any more problems on the network. And I've seen, we've been monitoring the network. I can see that it it is far away from to sustain a 40 gigabit with a system like this. And even if you want to grow it, I mean, it's really, really low. It's just hitting like above a little bit 10 gigabit per second. It's 12, 13 gigabit. And this is, I'm running up to 75 instances at the same time. And all they are doing.
That's one VLAN for everything?
That's one VLAN for everything. And I've never seen a problem with the network. And that's why we ended to build it like this. And they dropped all the VLANs and behind it. And I shared that with OpenStack community. And we had like a meeting like this, said, okay, could you please tell me if I'm doing something wrong? And since there is no HPC background, I mean, nobody complained, and we ended up doing it like this. Okay, BeeGFS. We started, I believe, last year doing some more serious work. The first time we did some work with BeeGFS, it's before BeeGFS. It was a Fraunhofer FS. And at that time, that file system had the limitation of the data. So it was not possible. If you lose a server, there's no high availability accessing data part. And that's what caused to, you will lose all your files that they are striped on that server. And that was a big problem for us. So we dropped it and said, no, we cannot use it like this. Let's wait. It had an advantage for the metadata. So they had an advantage for having multiple metadata servers, which is many file systems like Lust have not had it. But at that time, it was the data. And so we dropped it and said, okay, we are not going to use it until they came out, and now they have all these features implemented. So I believe, I'm not going a lot in details about what BeeGFS, just parallel file system, HPC oriented, use typical HPC network. And they're only developed by Fraunhofer now. I believe ThinkPark, they are doing a great job, I believe. Just have been growing a lot recently. And what some of the interesting features actually about it, well, actually these are the basic ones. So I'm not expecting here any special features. They have, you need to do some work when you have to implement, when you have to have multiple servers. So you need to know how to deal with the heartbeat and for high availability. But they still have some replication. So you can just, one way or the other, could just solve the high availability problems. That's all supported. They have it also for data and metadata. Quota is just supported. And I mentioned these two features because, you know, who use Lustre? How many use Lustre here? Okay, and do you have the problem of what we call the millions of files? I mean, did you have ever a user where he created like 5 million files in one directory?
We all have users like this.
Okay, and did you know, did you try to remove these, to delete these files? What you did? Did you format the file system? I mean, what did you do?
No, it just took forever.
It take forever, exactly. And that's so endless. Just remove, delete the directory with these million of files. It's a serial job that will go for one file after the other. And just imagine if a user made a mistake and created 25 million files in one directory, that's the end. You know, you really don't know what to do with this case. And this is for most of the, this is POSIX, and plus the serializing stuff. So Robinhood, for instance, this is one of them, one of the tools that we use for cleaning the file system, because you know you have 100, whatever the size of a hard disk, you always have data and you put it there, and this will grow. So at a certain point, you need to scan and see the old data. What I need to do, I need to clean it, because user will not clean. They don't care. Or you put a quota and force them, or you have to just to scan for these data. To scan, we use this tool, Robinhood. And that's taking 3 days to be able to get results, you know, until it's done. So that's a lot of time. So by the meantime, just there were a lot of data have been coming. So that's on Lustre. So this is one of the features we have seen it. The way it works here, it just we found some more intelligence behind. And this is, we found it some interesting way of scanning. Beyond these, this is quite interesting. I will be talking about this Beyond D as just one service alone. Easy to deploy. I will also just show one snapshot of what we mean. Because if you hear Marco telling you that's easy, I mean, just see the sales. So, yeah, we'll say yes and that's it. But why easy, and plus supporting x86 and open power? I mean, this is the open power part being recently, I believe, implemented, and we have tested it in our system too. So I'm preparing a script here for deploying BeeGFS actually, and in a way that you will just write down the name of the servers, and then the devices, and then you just run the script, and it will just deploy everything along. I just started doing it 2 days ago, and this is by installing the packages, just creating, formatting the file system, and adding these to the FS tab, whatever. Every step you do it, plus the tuning here. So these are all the tuning parameters included here to get really the best performance on it. So at the end of this script, I should be working in it hopefully soon. So you just run this. It will ask you for the name of the servers, the name of the devices, and then everything get done and deployed for you. At the end of this, it will be just ready, and you have up and running file system. You'll be ending up going to the client and mount it. So that's what we mean. And if you look at them, they are just simple, bash commands that you need to run it. So formatting ones, adding these to the FS tab, and these are some echo to in the kernel for commands. So it's really, really simple. That's what we mean by easy to deploy. Actually, I believe. I see it from a technical point of view. Yes, it is indeed easy to deploy. I won't say that BeeGFS is also just so difficult to deploy, because that's easy too. Okay, so Be on Demand. Be on Demand is one of the features that I really love, and I've been spending some time on it. So, is there anyone use this class on their cluster? So most of, I mean, this is really rare cases. Most of the people will be just having a disk on every compute node. And this disk, when you put the compute node, what happened? It will be just simply useless. You are not using it. It's just a disk sitting on a compute node, and you are not using it. The idea behind this is just we use every disk on a compute node, and we aggregate all of them and make a file system on the fly. So 20 nodes. I have SSDs in all my compute nodes. I don't use spindle disks. And soon I will be changing that to NVMEs. So what that means I will have 20 NVMEs just only used for booting and hosting some data for the operating system. Now, what the idea is I would like to have a user run through a scheduler, start allocating 20 compute nodes, creating a parallel file system used from these 20 unused NVMEs or SSDs. So we'll be having just what we call it a parallel file system on demand, and in a way that I will use these resources, and in the meantime, it will have no conflict with other users. It will not be affecting any other users, because I'll be only using the resources on my compute nodes allocated. So that's the idea, and that's how we can see it in a way that it doesn't require a root access. It is just only through the scheduler itself, and that's on the fly. That's the goal of how I can see it. Now, we are not there. As a root, I can do it, but still on the users, there's still some work, and I believe we discussed that. So that will be doing some more on the scheduler to be able to do it. So it's not limited to the disk. You could also use memory if you have a lot of memory, and it's like a shared memory only for parallel file systems. I mean, if you go back with what I talked about the NEC SX5 in 2003, 2004, they were using the memory actually for as a file system at that time. So it is just and all. Okay, we do not have a massive parallel machine. It was a vector machine with a lot of memory. But that's the concept behind having these fast file system in memory. It was there since a long time ago. I believe I covered everything regarding this part here. Yeah, and also I covered the benefits. So unused space, no impact with parallel file system. We just definitely use a high-speed network. I just love it when I see that just really with my jobs, I'm allocating most of the resources of the network. And it's not really there. I have 100 or 200 or whatever the number of the high-speed network, and it's not used. It's there, but it's not used. So it will make the concept of the high-speed network there is not really very useful. And this is scaling. Scaling with the number of, I cannot say because we have a limited number where we're testing it. So from the scaling point of view, this is to be discussed. When we talk HPC, we don't talk about scaling, but I remember I've seen one paper done at the Cray. I believe they managed to go to up to 300 compute nodes. So they used every SSD of 300 compute nodes, and they scaled with performance. It gave just interesting number. Now, the overhead here, that's an interesting. So how much are we paying from CPU? We do always would like to use a CPU for computing. We don't want to use CPU for doing something else. So the overhead is still really an open point. So profiling is just an interesting thing to do. And that's why when we started for looking for this, I've just recently, we'll talk about that. It will be coming. I believe I have one place for the showing some of the tools for monitoring and profiling the overhead on the compute nodes to really see what's going on when we are benchmarking a tool like this. So this is a system when we use when we tested the BeeGFS. That's not a B on demand. This is a typical BeeGFS. We had the DDN 7700. So this is really not the big system. We used FDR at that time. And these are the SSDs for metadata. And these are the data disk, spindle disks, and 2 servers. That's it. Here we tested, we use the system for 3 cases. We use it on Lustre, we use it on BeeGFS, and we use it on GPFS. And I will show only Lustre and BeeGFS. I won't show GPFS results. You can always ask me later why. These are the tuning actually we showed. These are the tuning that we use for optimizing the results. These are part of the kernel. So I put here the links for explanation for every part of the tuning. Okay, these are the monitoring the clients on the fly and showing what every client is doing from as a sum, open, stat, and this is you can do that with BeeGFS. So collecting data from the clients and from the servers is quite really easy and quite interesting. Just simple command shows you exactly every client was doing and every server was doing, and even every device. So if you have a lack of problem on the device, you know exactly where your bottleneck is. Okay, so you have also some graphics which have less interest in showing what's going on here and the kind of job running, and so I won't discuss these. These are the 2 tools that we use. This is for the data and this is used for the metadata. And these are our results. I want to use IOR actually, but I had a problem at that time. So we were just usually we use IOR also on this kind of test that scales more than IOZone. IOZone has a limit of 256 threads you can go, but IOR could scale more. So this is what we have seen on this system. So this is what the hardware is capable to do. So we got really the maximum we could do from the hardware. It's probably around 5 gigabytes per second. That was the peak performance of the hardware. So we were sustaining it. In write and in read, we have seen around 4.2 gigabytes per second. And just here we have rewrite and read. So these are typical tests for ISO. Now for the, that's where we've seen it more interesting for the MD test. MD test, what it does, it creates a file. You can tell him how much is the size of the file that you wanted. It could be 0, it could be just whatever, 4K, whatever you wanted. It just stated, it's the same for directories. It creates, deletes, state. It does a lot of these for directories and for files. And you can tell him how many directories and files you wanted to create. And this is how we were scaling. I don't know if you can see the numbers here. But here we are just started with 1 MDS, and we start going up to 20. And this is, we have reached, 100K IOPS on. And by the way, these are, I'm talking about showing results here with the B on demand. So these are the 20 disks that 20 SSDs that they were unused. And try to use this tool on your parallel file system and see if you can hit here 100K create files per second. So trust me, it's not going to be easy. So this is for, you know, free hardware sitting on allocating these 20 nodes, and these are the results for creating directories, stating them, and removing. Here 140K for removing directories. Okay, stating one is just more about memories of 900K, so I'm not really interested a lot, but I would like to see these two, creating and removing. Now I'll show the files actually, and this is what's happening on the files. So we're hitting 250K files per second. We are creating real files. It's not IOPS. So for metadata, it's different, IOPS than creating files. These are real creating files going on, and this is real removing files. So it's real metadata operations. So when you are deleting now, if you want to go and delete your 25 million files, that will be possible. Okay, at the end of the job, this file system, this Be on Demand will disappear. You know, it will be removed. So you need to find then one more step, which is just to move data to a parallel file system that you can keep this data and you call it back. But if you want to remove these 20 million or 5 million, whatever, you can do it here because we are just hitting that. Still, you need to use a tool different than RM because RM is serial, you know, serializing delete files. So you need something that more intelligent. So what's next? Still have 6 minutes. I'm almost done here. So what's next here? Scaling. Yeah, this is still a problem because I don't have a system. So my system now goes 2030. I'm just trying to work operation to see if we can deploy that in a bigger system and having access for a period of time where we can run all our tests. And hopefully that will be possible. We did not test the failover procedure, so all we have been testing it was only for seeing the numbers. So the failover is something to be done. Overhead, that's coming. NVMe, I ordered them, so I did not receive them yet, but this is going to come. So the NVMe is going to be interesting to see if that will scale. So I'll keep these SSD's results and then compare to NVMe and see if that will give us some advantage actually for changing only the hardware, or we have to do some more work on the software. Memory also, this is Lucerne. We are already discussing with many guys here. Yeah, Robinhood is, I believe we cover it. These are the monitoring tools that I was talking. So I'm using now CheckMK for monitoring, and these are all the features that we can scan and monitor and profile on every compute node through its agents. And some of these is CPU load, CPU utilization, disk I/O, whatever. And this is for one node, and that could be done also for all the cluster at the same time. So I can just pick whatever resource, especially the CPU and the memory. These are the two important parts for me, especially when I'm using Be on Demand, to see how much I'm paying CPU penalty and memory penalty on using these features of the BeeGFS. And I believe that's it. So if you have a question, I'll be very happy. Yeah, so I did not, maybe one more comment. I did not talk about GPFS. I did not show results of GPFS. We were close in results between Lustre and BeeGFS. BeeGFS gave better results, sustaining the hardware. And I called DDN because DDN, they are one of the contributors in Lustre, and they tuned it. Everything they could do, they tuned it. And we never reached, BeeGFS gave a better results. Now, GPFS gave bad results. I did not, it was extremely bad. So we have 5 GB, we went down to using 8 MB block, I managed to get 2 GB per second. And if I use 1 meg block, which is what I was using on GPFS, on Lustre and the BeeGFS, it was like 500 MB. And that was extremely bad. So since we did not have anyone at that time from IBM to tune it, we said we cannot show results. We need to verify that. It could be some configuration problem. And so we did not we wanted to be fair with every product. And that was the main reason.
Yeah. So In slide 18, I think you mentioned about these SSDs that are just sitting there doing nothing. Yep. First of all, I don't agree with that statement. I think that is not really true. There is a bunch of libraries that are using local storage in compute nodes and doing, fast checkpointing and then offloading to the file system asynchronously and this kind of stuff. So I don't really agree with that statement. But regardless of that, I think the idea of building a file system on these SSDs that are using compute is a really I'm not going to say a bad idea, but it's a very challenging thing. Based on the requirements that a file system has, like consistency and data integrity and all these, you would have to think about RAID systems, encoding block of data, which processor are you going to use to encode these data if you want to do this distributed file system across the SSDs. This is a really challenging thing, and I understand you point out and what is going to be the overhead about doing this. And furthermore, if you plan to explore this into non-volatile memory, there is even I would say a more crazy idea, because then you might have a byte addressable non-volatile memory, and you don't really want to start moving 16 kilobytes of data every time you want to access this thing, and having to pass through the operating system and execute thousands of instructions to access the data in this non-volatile memory. So what are your views on all of this?
So actually it's not a question, it's just a comment about it, but I will just be answering part of it. So we have a file system on the Cray machine. We have a file system that could deliver up to 120 gigabytes per second. Okay, and we were seeing very, very, very low numbers from customers, and we were just discussing that with the users about the way that they're using. I'm using here a benchmark tools, synthetic benchmark. So I could scale, and I am giving good bandwidth because I have big block. But from the application point of view, you don't know what's happening. When you're running the application, you are just writing and reading, but not all, very little people know what the application is doing. So we start profiling one code, CP2K, which was optimized for doing a high I/O. It was modified by the developer to do some high I/O, and he said that he will be taking the file system on its knee. He promised, and he never managed to go above 20 gigabytes per second. It's 120, and that's what he did. And when we start profiling, see what's going on, his CP2K was writing 256K as a block, or I'm sorry, 256 byte as a block. That was the size of blocks that he was writing. And he was parallelizing. He was using the entire machine parallelizing. That's why he managed to get 20 gigabytes per second. So the main problem with parallel file system is that we need to use big blocks. And when your applications writing with 256 byte, you will never be able to scale. You will just be hitting, you just do whatever you want, your performance will really be extremely bad. That's one. The second, you will be just doing some random I/O. And random I/O with spindle disk is very harmful because you have what we call it secret C. So that means there's a penalty between every read and read, because it has to go from one point to another in a spindle and come back and give you results. And this is really very bad for accessing data. So all of that making the parallel file system, to give a good numbers on real application, like whatever the application it is very bad. So we had to look for something crazy, as you describe it, to see how we can improve the application itself, and see how much I'll be paying from CPU penalty. That's one part of the reason behind why looking for alternative. And one of these is the IME caching mechanism. It's just similar cases here, what we are doing. That's one. The second point about the disk, what you are doing, I can tell you, I'm running, it depends on the kind of application you're running. So it could be, that's very true, that in some cases, it will not be very helpful. But in most of the cases, if you profile on monitoring the node, what's happening on the I/O disk locally, on a machine that's up to 5,000 nodes, you'll find that they are doing almost nothing. They are just sitting there, because when you are doing checkpointing, you are not doing it locally. You will be doing it in parallel file system.
Not necessarily.
So it is for Hadoop, when you are doing locality, you can do that, which is here a different case. Here I'm taking the parallel file system and using a case like where application is using the parallel file system as the main resources for. Because, for instance, our Cray machine, there is no local disk. We have everything is sitting in the memory, and the memory used only for the OS. So there's no local disk. Everything has to go to parallel file system. That's when we're talking about a scaling machine, a big machine. So we might be taking part of it being B on demand. Plus, when we are creating this file system, we are creating it on the fly. At the end, when you create it, you run your job. At the end of the job, you will delete it. It will disappear. So it's not that I will not keep data there. It's just only the moment for the job, it will be going up, creating it, and then deleting it at the end of the day.
But exactly, for this very same reason, you don't need the same features that a parallel file system will offer. You know, for using this local storage, sometimes you don't need, you know, global data consistency. Sometimes you don't need even, I don't know, a reliability. If you are using a Monte Carlo application and you just write some data very, very fast, you don't have to go through a file system to access this storage. And you may not even need to have this block of data stored reliably because you can lose it depending on what you are writing on.
I did not talk about reliability here. Many of these features in parallel file system that could apply in the B on demand. What I'm saying here is that we need the performance, we need access to, we need to be able to read and write a lot of files in a very fast way, use the network very well, and just try to avoid overheading the processor as much as possible. I never talked about consistency in the B on demand, because even if I lose all data, I don't care. Because the moment I will lose one node, my job is died, and the B on demand died. So here, we don't care about even all these features that are implemented in the parallel file system. These are extreme, they are out of the B on demand.
Yes, Jordi.
More a comment than a question. So in a cluster, what we usually do is to allocate per CPU core and memory. The beauty of BeeGFS, BeeGFS on demand, is that you can allocate also cluster file system per job basis. So so we talk about these kind of users that are challenging you every day or every second in your data center, by creating millions and millions of files and annoying millions and millions of users that you have to share this cluster file system with. Yeah, so it's quite a challenging situation. By creating this cluster file system on demand, you allocate this kind of behavior, these IO patterns in this specific cluster file system. That's going to be there just for the lifetime of the job. So if you lose something, one node or whatever, if the cluster file system crash, you're going to impact just one job of that. So that's part of the beauty of that thing. And I have to say that these results that you have showed there about metadata that show, well, for many people looks amazing and really, really impressive. This is BeeGFS on demand. But with BeeGFS, the metadata operations, once you apply some tuning on top of that thing, with this amount of SSDs, usually it's even higher than that. So this is what we have experimented as a consulting company in this area. So, and I have to say that I'm very, very, very jealous about your setup, that you are able to test every single technology that you have in the market. So it's pretty good to compare. So.
Yeah, definitely. I mean, we focus on the B on demand for testing, especially for metadata. We have been lacking for years and years. It's like a wall on a POSIX, the metadata part, which has created the big problems for everybody. Anyone who has a big system, whatever the parallel file system it is, we used to have this problem, and scaling, and users will, oh, I would like to have 1 million, 2 million because I have this kind of code. So we said, okay, change your code. You know, and that was simple. So it's just like, that's not a solution. We have codes that we know that there are codes now, especially with everything related to machine learning. They require millions of billions. I mean, we have NVIDIA now systems sitting in a car and they do some computing in recognizing pictures and just the self-driving cars, and that's the engine behind. And so every image that will collect on the street, they should have a database in the background, or they should not be capable to recognize what is this image behind them, and that's required enormous amount of data from simply cars.
Have you asked your users what metadata consistency they would be satisfied with, and like whether they really need full POSIX consistency? Because I mean, most of our codes just open a file and write to it, and then and you don't read from it again. And you especially don't read from it again on another node. So I think it'd be interesting if you're doing all this testing to ask to look at the applications and see what they're doing and see what you could settle for. Because that might be useful for the people who are maintaining the parallel file systems.
Yeah, I completely agree with you. This is one of the biggest problems we have with researchers. I remember I sent one email once to the researchers, said, could you please tell me what's your requirement from the storage point of view? I mean, from data and metadata. I never got an answer. Nobody replied. I sent it, I promised, to all at CSCS. So to be more, so I sent it to Ulish. I said, okay, could you please share this question with all the guys in Ulish? It was the same case. Nobody answered. So it's really difficult to understand what the application requires from data. We will only be hitting the problems, and then we'll start trying to understand what's going on and what's more or less the requirement. It's always that we need more space, I need more bandwidth, and I need more accessing how fast I could be data and metadata.
I mean, I think most of our users only need the POSIX consistency because they use ls in a directory to see how far along their job is. Like that's
I think POSIX is, we all hate POSIX, but I don't know if we can just get rid of it. Now, object store is just one of the solutions could be answer many of these questions, and we are doing a lot of work there. Hopefully then we'll see some work there to be done also with parallel file system, with object store that will be able to write itself.
Yes, that's a very simple question. You say it's very simple to install it with this script, but I guess that you should have some parameters to tune. How easy is to tune to use these parameters, or how robust is this in this sense?
Okay,
it's just like this, I've never.
Yeah, the tuning parameter, the one I use, it was in our case, and I think that's going to be case by case. And there is no receipt. There is no ready receipt. What you need to do is just take, if you want, I can share what I have from tuning, and you can try to run it and see what you can get, especially when it has to do with cleaning the dirty that remains in the system. Then what you could do, you could just try to change these parameters up and down and see how much it has impact on your system. But I believe that's case by case. Depends on many.
No recipe then.
Yeah, there's no recipe, no, not at all. But this is a good start, I believe.
Okay.
I think there's one question. Yes.
So I was wondering, because we have started a really nice discussion here, maybe it's time to move towards to the roundtable and allow other people to join the discussion as well. So I would have to encourage Intel guy and IBM guy to. And yes, for sure. The question that was over there, I don't. Pablo, sorry. Have a seat.
My question was, if you use BeeGFS on demand, this has to be dedicated for BeeGFS on demand and cannot do anything else, or you can have a different job writing some data there, and it's only a subfolder in this which is used for how it works.
I'm not sure if you can use the be on demand on other nodes. I think it should be possible, but the nodes that get allocated. So if I understood well the question, this is if I create a file system using 10 nodes, is it possible to use this be on demand from the node number 11?
No. If another job in the same machine, I have two jobs.
One
creates the file system and another wants to write to this disk. Is this possible?
Yeah. So that's when you are what we call it when you are allocating the machine. Usually when you're running through scheduler, you run one job. But if you are allocating allocating the node interactively, yes, you can do it. That should be possible. Yeah, that won't be a problem. And even multiple. So you can decide on the Be on demand what you want to do at the end of the job. Do you want to kill it, the Be on demand, or you want to just keep it for some more jobs? That's also some of the work. We need to work on the scheduler because that's still an open. The scheduler part is not completely finalized. We'll see what we can do with
What's my next question? Was the status of Slurm?
Yeah, so the Slurm part, because we are using Slurm, and this is still, we are doing some more, so hopefully that with some contribution with the community, and we'll be just following with think part, we will see how that should be hopefully ready soon, this year, hopefully.
I have another question related to this one. So the backend storage that you use in the compute nodes, do you have a dedicated partition for that? Can you use simply a directory?
So the backend of the Be on demand is the local disk.
Yeah, but
okay.
local disk.
You can use as a partition. You can use a partition. You can use it also because you want to use part of it, not all of it. Otherwise, you'll get full. And then if you have a full disk in a compute node, that's bad. Not a good idea. Because even directory, that could be a problem. Otherwise, it would be dedicated partition. Or you can use also directory. So it has some flexibility, but you need to be careful about not to make the file system full 100%, and then you have a different problem.
Okay, thank you.
More questions? Other than just BeeGFS on demand? Come on. So usually these situations where you have a user or a kind of jobs creating a lot of drama in the cluster file system, it's really hard to recognize for most of the cluster file systems. I was wondering, this is an open question for Spectrum Scale and Intel, and well, you are not representing BeeGFS, so probably somebody else around here can answer that thing. Okay. So okay, that's fine. So, well, the thing is that one of the main concerns here is that it's really hard to identify who is responsible for this drama in the cluster file system, or which subset of jobs are responsible for this unhealthy situation. So some cluster file systems are able to provide per user statistics. Some of them per node statistics. I have seen none of them, or any of them, able to provide per job level statistics. I know that some HPC facilities are doing kind of collecting kind of statistics per node, and they are allocating job per node basis. So I'm afraid that this is case of attack and many others. But those that are sharing resources between the node, so I mean, a small number of CPUs are located just in a single job, and you can have multiple jobs in the same node. Then it's a really challenging way to deal with it, and usually not getting statistics per user. You can point a finger to the guy that, but it's even better to see the I/O patterns per job basis. So, John.
I'm not aware of any statistics per job or per user within GPFS. Don't know on the other Lustre or BeeGFS. But I was missing one question to BeeGFS. If you had the chance to run on these LES, wouldn't you have taken the same performance from 20 SSDs on a centralized storage?
this is one of the key tests that we'll be doing. And this is not only applied to be on demand, but it's also applied to any caching mechanism like the IME or others, or WARP from DDN, from Cray. If we get the same results, then we have a big problem with the software. It should scale. And this is what I believe BeeGFS, they just announced that it should be scaling with, it will be hitting somewhere a limit. We don't know where, but so far in our case we'll be using SSDs, NVMe, and then the memory. And that's where we'll be just comparing. That's why we said okay, in our testing we'll be using this TMPFS, which is using the memory, and we'll see if we'll see a real difference that sustain the hardware. What we'd like to see that not as a problem of software. We would like to see that problem to the hardware. Hopefully that we'll see it. And if this is a case, that will be good. But I cannot, yeah.
You will reach a problem with the scalability when the number of nodes.
Exactly. So scalability will be getting 20 to 30 nodes. In our case, that's the maximum I can reach. I cannot go beyond that, but hopefully that in the future we'll have, I don't know, if we can get the good results with 30 nodes, then we'll start looking for resources where we can go at least 128 nodes or 64 nodes. Yeah, that's the idea.
More questions? We have time.
To get back to Jordi's question, you said there's no user level, let alone job level statistics in GPFS. But then what is a good way of figuring out who is causing the problems? Is there a good way? Is there like an approach you can take to quickly figure out who's causing the issues? Because it's an issue that we are seeing a lot, and it's not always GPFS's fault, it's usually the user's fault. And very often they're just not aware that they're doing something stupid.
This is more on the scheduler side than the
It's not really the scheduler, it's figuring out who is causing the load that is making things slow. No, not really. You need to know where the load is coming from. Just which nodes and which account is causing so much load.
So I will take this too. That's on the behalf of GPFS. So we had a case where that was on the power machine actually, and we have seen from time to time some of the NSDs were just going down and having problems, and we were trying to figure out what was going on. And we figured out that one user, we had to profile, we had to really go and deeply dig in this problem, and took a lot of time to understand. And we figured out that one of the users, he was using the parallel file system as a swap. So he was swapping what he was running on the parallel file system, and that was taking GPFS on its knee. And that's by profile. That's exactly what you said, going by job, and that's looking in every job what's going on until we figure out. And we're profiling every node and see what's going on until we figure out that one of the nodes that was like getting crazy. I mean, just multiple of nodes. One of the jobs, sorry, was just getting crazy, and that was taking down the system itself. So this is a case where we managed to solve.
So the issue is that there is no link between those loads in the compute node with a job ID, for example, or the user.
Yeah, that's something, but at least it's better than what we have.
We have that with the the plugin that I presented in the HPC knowledge meeting last year that sends the slurm metrics to InfluxDB. You have that info in the reads and writes from different. You cannot differentiate the file system the job is writing, but at least you have the read and write megabytes per second from each individual job. And that has helped us a lot figuring out what is going on especially because in bioinformatics, users tend to submit plenty of serial jobs, so you end up with 24 or 36 jobs in one node and figuring out exactly which one is affecting, because identifying the node is easier with these IBM tools, but you need one step further to get there. And with that plugin, at least we
plan, by the way, once we have file system monitoring, we plan to do that. Once we identify the problem, the node where we have the issue, try to search for each of the jobs running there. It's not a perfect tool. It would be nice that a single dashboard manage everything.
It's a problem of correlation. The info you've got from the job scheduler and the info that you've got from the file system users. Putting things together.
So this is maybe for the vendors and also for the community, and see how we can deal with this kind of problems. So if I have a good network, I have a good parallel file system. This is the rule. If I have a bad network, whatever file system it is, I have a bad file system. So how it's possible to identify network problems through parallel file system? Because the first thing you see when you're running a job and you have any network issue, the file system will go down. And you run df, it will log. And then you will just start looking what's going on in the file system. And in Lustre or GPFS or any file system, you will be just getting some kind of error that it is just, I don't know, written the time of the Egyptian. So it will be difficult to identify. And see, this is really a network problem. So how that could be improved and how can that be identified, especially for GPFS and Lustre and also BeeGFS, I believe.
What's more, it's a kind of correlation of the network statistics you've got from the manager of, for anyone to be UFM or something like this. And
I think we need some more development going there.
Yeah.
On the system to be able to give more, identifying more problems. If you look at the Lustre logs, it's impossible. You have hundreds of thousands of pages with really difficult to identify. It's like OpenStack logs. It's a lot of data just generate. So we need something that could be identified from the network point of view.
Not from the network, but I was to say analyzing logs and applying machine learning to this would be a way to solve. I was told about this back yesterday. Some guys that did predictive analysis of how to use HPC resources in order to offload to cloud and know which data will be needed in the cloud to process some parts of the job. So predictive analysis of logs probably could be one way to solve it. Don't know what you were about to say.
Yeah, I'm Marco from ThinkPark, and I'm reselling the BeeGFS stuff, so maybe you don't know that, but I want to bring also to the audience here that the product line Minsky is certified on BeeGFS, so we did in Montpellier tests and certifications with the IBM, HPC, Open Cloud people, and I do have also some scalable informations with me, so I put the scalable performance tests in front of this BeeGFS things, so you can have a look on it, and you can also talk to the guys in Montpellier, so we are happy to assist you.
So a lot of difference on performance between
it's more easy, and the thing is also you can start really small with BeeGFS. You can start with really 2 storage nodes and scale up then if you grow by capacity and performance demands. And that's the reason why we are partnering, and we are now also a member of the IBM Open Power Foundation.
Another question related to file system and storage in cluster, because I see there is some advance on encryption of data and security, and this I see the request coming from the life science people, try to analyze patient data or doing more secure environments. And is there any way or any tool, any available approach to get detailed access logs to the data? Like a tool giving me this data set has been accessed by this user at this time. I know it's not easy, but is any feedback on this or work done on this direction?
So any more questions? So nobody is concerned about the small I/O patterns and the performance? No? Can you comment anything in this regard from spectrum scale? Or from BeeGFS? Intel guy have run away? So next time around you. Well. So one of the usually the big problems that many HPC facilities also have is when a user tries to generate a lot of really small files in a shared cluster file system, or to read them all when you have a lot of them. So it's kind of a intensive metadata operations, but as well I/O intensive. It's not a limit in the network. Network can be something rather commodity, but at the same time, the performance that you get out of there, it's pretty bad. So I have seen some work from Intel trying to do data in metadata, to bypass these operations. BeeGFS performance looks quite good in this regard, but it's even better when you have BeeGFS on demand, because you have the cache in the same compute node. But once you have that thing into a remote node, so it's actually the same problem. It's a common problem, and we have those kind of users. So you can replace the users, I guess. So, well, maybe.
One of the places where I've seen that they have a way of dealing with this, at least partially, when it's about reading lots of small files, is they just pack them basically into one image and then access the image. So you basically, it's all internal. This is one of the advantages of singularity. If you pack everything in a single container image and then you just run inside the container, the file system doesn't suffer. It's basically one file and you're just accessing stuff in memory. So that's one way, but that's mostly read-only. If you're writing files, it's a different story.
So we have seen a lot of good feedback from the community while using containers inside an HPC facility, because you have just a single loopback file, and all the small I/O is condensed and allocated in a single file, but then you have the problem of data locality, so it's not going to be able to share across the cluster. So similar approach with overlay-FS. If you mount union-FS, for example, on the user space, you can deal with you can recover this cache as well, but then it's only used in that particular node. So I'm not sure if Carlos, because you have been working also in union-FS kind of a technology, is it able to provide a kind of a distributed layer to?
data on metadata you mentioned, it's possible on GBFS, but the file must be really small. But this is something, it's possible.
It's enabled by default in GBFS. But the inode size in GBFS is quite big for scale.
Yeah.
So everything that fits in the inode is stored in metadata server. So for really small files, it will be served by the metadata. The main problem we have is they have small files, but not small enough. They are around 16 KB. And lower than and they have plenty of those, so yeah, reading on all those parts is going through.
Just to look at something that sits between the metadata and the data, which is like this kind of size. It's bigger than 4 and less than 64, and sits in a layer or whatever, that's also
So if there is no more questions or comments, we can go for lunch. We can, Juliet, where...
Yeah, well, it's still raining.